Okay, is everybody done? All right, let's hand it over. I'll get this around these. Are you done? Okay. It won't be lost. It's sure okay. Alex is here as well. Okay, I got everybody. Okay, how do you guys feel the quiz? Pretty straightforward, huh?
Does it mix or does it not mix?
I cannot tell you, because I don't know. I just written random numbers and chi's. So let's see. But I guess will not, although I haven't tried. Polymer with such a high chi value? Not likely. No, we still have one. Sonia will be coming in probably in a moment. Before she shows up, let's have just a recap what we talked about last time. Okay? So, osmotic pressure is the last topic we discussed. And this is the first parameter I kind of showed everybody. This is one way you can measure the solvent quality now, because the second viral coefficient is some parameter you can rely on to say, is your solvent a good solvent or not good solvent or theta solvent? And those two figures are most critical, okay? Those two figures in the slides that shows plots of osmotic pressure versus concentration, as well osmotic pressure divided by concentration plot as concentration. Those two are the most important, because they have practical use. They're going to be a homework help you guys to understand this better. And we're going to have some homework after today's class, okay? And I feel like I received a lot of feedback, not in a good way, saying like, Dagu, the homework is so hard. Can we actually do something better? I think so. I'll make you guys' life easier. So I'll give everybody an option to skip one question out of 6. Okay? If you feel this is a terrible, I really don't like this, you can pick that one, say, sorry, this is the one I chose, I don't want to answer that particular one. Okay? Sounds fair?
Fair.
Okay, so with that, I hope then everybody will feel a little bit more comfortable for the homework.
Will it be homework out of the textbook again?
Yes, of course, that's the best. I do think that the homework on the textbook, although it's hard, it's beneficial if you try it, because what it's designed is help you to understand what is written in the textbook. And the polymer chemistry is indeed a very good, textbook. It's very well written, very simple to understand, right? So, 1 second. All right. Okay, so any question regarding osmotic pressure parts? Should be straightforward, right? So I also want to touch a little bit about where we left. So we talked about how to understand osmotic pressure using a regular lattice theory, doesn't consider the polymer, and just to use thermodynamics to kind of calculate what is osmotic pressure dependence of concentration. There is a second way actually can achieve the same findings just using the Flory-Hagen theory. So if you go back to the textbook, there is a section talks about how we can use Flory-Hagen theory to back calculate the osmotic pressure, right? So I'll show you guys just in 1 second. Well, in these slides, basically, the second way of understanding the osmotic pressure, you can link this partial derivative in terms of chemical potential would be equal to free energy, partial derivative to n is molar of your polymer. So if you take that one, if you want to get the partial molar derivative for the free energy for the solvents, you basically need to use delta G, partial derivative N1. I'll show you guys how to do the derivative in another separate video, because I do think it would be fun to do in class, but kind of boring, spend 30 minutes to go through all the derivative, okay? You can do it, because if you go up, look at what is delta G. Let me stand here. Everybody knows N1 is related. If you take a partial derivative in N1, phi 1 is also related to N1, right? N2 is 1 minus N1, same for here. So if you take a partial derivative, which as I mentioned, I'll post the video to show you how to do that, you would be able to directly get this A2 relationship with chi. What is A2? Secondary variable coefficient. And we discussed a lot in the last lecture about what is A2 specific mean, right? Everybody understand the physical meaning of A2? Larger than 0, A2 smaller than 0. Correct? Larger than 0, good solvent. A2 smaller than 0, this is going to be and they're going to be equal to 0 is the Zeta condition. So now, take a look at what A2 relate to chi. Anything you can find? Any trend you can find? Or anything we can say about this? Can you say it out?
A negative linear trend between the two of them?
Right. They're definitely related, right? So those two basically constant. We're not going to talk about absolute value, but we're just going to focus on 3 special conditions. When A2 equals to 0, what would be the chi be? Correct? When A2 is larger than 0, chi? Less than 1/2. Make sense? And there's one more definition. So this would be what we can learn from Flory-Hagen theory. How does different solvents quality relate to different chi value between different parameter? Okay? Any question for this part? So chi equals to 0.5 is something very special. Zeta condition. And a lot of you might wondering, what is 0.5? It's kind of a random number, right? Because it's either going to be 0, plus or minus. That's more intuitive. Think about interaction parameter, which we will cover in another later part of the lecture, okay? So if you go to the textbook, read about 7.7, it will tell you what is the chi parameter, and we'll go there and study that. It's not there yet. But this actually links to you give you another knowledge about chi parameter and give you some physical meaning or relative value to understand what the chi is. Make sense? So if chi is bigger than 0.5, that means it's really large unfavorable interaction. If chi is 0, much smaller than that, that's usually is good. Please.
I have questions.
Yes.
Chi was defined by delta W times like latex constants and over like KT some Boltzmann constant and temperature.
Yeah.
You know, like we have different latex constant.
But it wouldn't change. That's right.
And like the temperature also vary.
Yes. Chi is certainly dependent on temperature.
Yeah, now like chi turned out to be like a fixed constant to like convey us some idea like if chi is like negative or if chi is like smaller than 0.5 or chi is larger than 0.5.
Right.
Identify as a like good solvent or bad solvent.
Not necessarily bad solvent or good solvent. It just gives you some ideas about interaction between one species versus other.
Right.
So if you think about this way, if you have a polymer in the solvent, remember we have polystyrene cyclohexane. We did an example that at different temperature you would have different behaving osmotic pressure. So that's partially explained to you what is the chi value would changes with different temperature. Okay? So chi is not a constant. So let me see if I can go back and we can take a look at this, not this one. This is not a chi relationship. One second. So this is what we originally defined what is chi is, right? So Z is lattice parameter divided by KT, and delta W. W is interaction force between 1, 2, and 1, 2. Here we very much simplified all the conditions to be ideal. We didn't consider other things, for example, the long-range interaction. In this case, only talks about 1, 1. Very close, right? And we defined a Z parameter. So this is a very sort of preliminary stage, but in reality, when you measure it, we would be showing chi would be equals to, if you remember, chi would be equals to a something like that. It would depend on what the relative value in A and B is. So temperature would be impact that. So this comes to a question that chi depends on temperature, and you cannot just say chi is constant. Okay. Where we are now, almost there. And one last point that we can actually really do is experiment is basically get what the concentration and measure osmotic pressure, then calculate what is N divided by CT. Osmotic pressure divided by CT plot as concentration. This is an example, real data. You will go through the simile in the homework where you can actually get what is Y equals to a certain X value. And this would tell you what's the molecular weight for your material, which shows the intercept and inverse. Okay? Right? We all know this will be equal to 1 divided by N plus A2C. So this A2 is basically this slope where given by the prefactor before X, and N is basically the inverse of this intercept with the y-axis. That makes sense? Okay. Well, I'm wondering, I probably should make a break to check out where how's Sonia doing. I don't want to leave her behind, so I'll go check it out and I'll be right back. Okay? Just make sure we don't leave behind another student.
know. That's why I'm thinking too.
Oh, yes.
Okay, well, almost everybody is here. Okay, so we're gonna do something more interesting today. It's gonna be chapter 7.5 talks about, or 8.5 talks about phase diagram. This is probably the most useful chapter for the whole class. We're gonna teach in chapter 7 and 8, okay? So phase diagram, what is it? Somebody tell me?
It's the diagram between pressure and temperature that gives you phase changes.
Phase diagram basically tells you what's the phase, right? Phase diagram. What are the typical plots in X and Y?
Or
What is those two axes in a typical phase diagram?
Oh, pressure and
temperature.
temperature.
It can be any. It can be temperature or can be pressure or can be anything. But for the sake of discussion, we just talk about temperature in this class. Okay? So vertically is the temperature, and horizontally we're going to have what is in the horizontal axis? Concentration for each component, right? It's quite different in the free energy, but think about this will be, we are mixing A plus B. We're going to mix two of them together. Still hard to see, Lena? All right, let me shift it over. Temperature, A, B, we're going to mix them. Here is 100% A, or we just call it a B percentile. We can just say 0% of B to 100% of B, okay? Volume fraction. In the middle, 50-50. So what we are trying to explore in the phase diagrams to understand if your material will mix or not mix. Like the test or quiz we did is we ask if this is potentially going to mix or not. So in a given temperature, we can calculate, right? So if we fix one temperature, like we did, we say it's room temperature for your blends, then what we can get is basically calculate if there's A, if there's a B, we can get what they will mix or not. This is one way you can do it, so you can calculate it out. If you do everything, there are potentially several ways you can get into the phase diagram. Let's just show you a typical one. Under this area, nothing will mix. And above that, it's called a one phase, where everything will mix. So if you want to check this polystyrene, this polyethylene, and let's say this gives you the temperature scale, you check 75% at 50 degrees. If it's folding here, that means they will phase separate, okay? Very easy to use the phase diagram. But how do we understand and how do we make it a phase diagram? Not that hard. Not hard at all, because the fundamentals we already learned. The fundamentals about the interaction parameter between different phases is all talked about in two-phase system, right? We know if your material will be mixed or not mixed, like we do the test. Before I go into too much detail into that, let me first define several different terminology in terms of mixing. In the thermodynamics, if there's only one working definition of miscibility, if there's a single phase in solution which component is intimated at molecular level, it only forms when delta G is smaller than 0. which means they will be spontaneously mixed. Okay? So it's literally, we just need to understand the dependence of delta G on different temperature, can construct a phase diagram. Because previously we don't talk too much temperature, and in this class, temperature is becoming more important. And if you recall, let me get, okay, I'll use a different color. This would be fixed at a given temperature. This would be no. Temperature would be also a deciding factor to determine if you're going to mix or not. So let's have several extreme cases. Well, if temperature is infinitely high, it will likely to promote the mixing. Well, if the temperature is infinitely low, then it's only dependent on delta H. So in the typical temperature range that a human being going to be exposed to, that's where our interest is, at 0 degree maybe, up to 100, 200 degree. Anything extreme than that, it's very hard to deal with, right? And one more term I want to define is, think about this as energy for the system. Okay? You can think about potential. Let me show you example with a brick. So if I take a controller, put it this way, let's don't do that. Maybe I get something that's not expensive. If I drop that, I'm gonna probably use my salary to pay it. This one. It's example that when I lose it, it will fall down because the potential of energy is lower in the flat state versus the vertical state, right? And the system would spontaneously go to lower state because gravity actually works on my eraser and make it lower energy state. And how about this state? Is it stable? But it's metastable. If I shake it, it will give it some disturbance in the energies. It will go to allow it to pass a critical energy point, which is it need to go a little bit tipped past that maximum, right? So it's sort of, you can think about eraser going vertically from the side is pretty much like this state. If there is a small disturbance in the energy, if I say make this eraser excited to wiggle, if the small wiggle, if it goes to here, it will still relax back because that's like local minima for this range. However, if I shake it really largely, it will pass this energy potential to reach to the lowest energy state, right? So which is here. So if you understand this will help you to understand the lecture about phase diagram, because we also going to be experiencing local energy minima versus global energy minima, okay? So when you think about that, think about the eraser case. Sonia, please.
So does the metastable condition have a direct impact by surface area then?
You mean in my case or in the phase diagram?
I guess just in general, because it seems like whichever side has the small surface area is going to be the one where it's the least stable to be like supported by, right?
This is a question I never heard before. Can you ask it one more time?
Does surface area have a direct impact on this how stable a metastable component is?
Well, I think in the phase diagram where we're going to talk about, the surface area is not a critical parameter we're going to talk about. But in some cases that surface energy or surface potential is one of the driving force in the mixing, because you want to minimize if two phases, if they don't like each other. So think about water and oil. If they phase separate, they're likely to be phase separated into two phase And of course, gravity also make a difference. There's a phenomenon related to that called Oswald rippling. So if you have polystyrene, polyethylene, they don't like each other, they're going to phase separate. And let's say you spin coat from the film, they form nanodomains. However, when you heat, they will continue to grow to minimize surface contact between two phases. However, not related to what we are chatting now, okay? More stuff.
In the phase diagram, so you
Yeah.
have two phases or one phase. In the line, on the line, is one phase or two phase or in between?
In the horizontal line?
No, this line.
What line? So this line.
Yes.
So we're going to just go into that one, okay? Good question. So this defines several different energy states. So let's say this would be the phase diagram, and then phi 2 is just a volume fraction of minor component, T is temperature. There are probably a lot of questions regarding what is this gray area. Let's leave it to the last. So let's first talk about this region in the center, and I can use my pen to highlight them to be red. Okay, so this region. Everybody got it? So this region is basically two-phase. If you mix 50-50% of your material and fall into this particular temperature, it will be two-phase. You raise the temperature, it will still be two-phase. Right? Until you raise the temperature, fix, let's say, 50% mixture, you raise the system temperature. Effectively, what happens is you walk around the line going up. Now I exceeded the confinement area. You would pass some temperature point called TC, which is called critical point. What that means is anything in, I don't think I can change the color, so I'll go for the other direction. In this area, it will be one phase. Okay? Go in the other direction instead of going the other. One phase means no matter what temperature, it will be intermittent mixing. So we can read the phase diagram in two ways. First is going horizontally. This data point, let's say here, means I have 99% of A molecular, 1% of B molecular, they will mix. If I keep going, 75-25, still going to mix. This is still in one phase. Once they hit the binodal, this is called a metastable state. It's temporarily stable, but it's not permanently, okay? It could have something like nucleation and growth that causes them to phase separate. And here is where it's totally not going to be stable. Like I showed you the eraser, it was just going to fall. And what's going to happen is it will become two stable phase. Waylon?
So, are eutectics considered to be metastable? Like eutectic mixtures? Or does that fall into something completely different?
I'm not totally familiar with that term, to be honest with you. So let me check on that and get back to it in the next class, okay? So in this phase, it's going to be just a two-phase. Nothing mixed. That's one way you can read the phase diagram. If you have only a little bit of A and B or B and A, they're still going to be mixed. So there's another way you can read the phase diagrams walking it vertically. Let's say you fix, how about we start from here? 40-60 ratio. So you have 40% of B and 60% of A. You cool the system down from high temperature. In high temperature, it will be one phase mixed. When you slowly cool down, it will start to phase separate. Right? That goes through the metastable phase and it will be unstable. And in the spinodal phase diagram, it means it will be spontaneously phase separated into two phase. Okay? Two phase could be one phase rich in A, one phase rich in B. One of the simple example I like to give is just a water in oil. Okay? At some range, they can be intermixed together. At some range, they just go on to phase separate. or more commonly, this is going to be polymer solvent or polymer. Well, any question about this simple phase diagram? Great. Everybody knows phase diagram. Yeah, Sonia, please.
So you said with the one phase that it's going to be mixed, not dependent on temperature. It's always just going to be mixed, right?
So look at this phase diagram. As I mentioned, that we have two ways to go. Temperature is, of course, very important. If you're above this TC or critical temperature, you can see if I now, this is a Professor Gu, he's a Superman, can dive into this frame, and he can go around this one. He always stays in one phase, no matter what mixture ratio you want to say. So TC is one of the critical points because above TC, whatever ratio you want to have, it's always going to be mixed, right? So you go down the temperature, then it depends on the mix ratio. In this particular phase diagram, in the middle part, 50-50, they're not going to mix. But if you take something out, they're going to mix. Okay? Lena?
Just to clarify, the gray is where you're in.
The gray is metastable.
Okay.
So you can be one phase, but it's not at equilibrium.
Yeah. It will be locally stabilized until you have a large disturbance to the system, then it will drive it to phase separate. Okay? So like, where's my eraser? Okay. I better find it because that's best example. This will be the sample in here. If you don't touch it, if you don't shock it, it will be stable. But if there's a large, let's say, thermal fluctuation or external stimuli, which allows us to, not gonna happen. All right, I give it a stimuli. Now it happens, right? Now it's gonna be phase separate into two. That was funny, huh? Is it clear? So this is also called, unstable is also called spinodal curve. This particular dashed line is called spinodal curve. Spinodal means when you first see when they're going to be phase separate. In spinodal curve, we can actually figure out a way to calculate it. And as long as we calculate our spinodal curve, anything in between will be non-mixed. Clear? Sam?
Is the metastable phase unique to polymer systems, or can it also apply to just simple mixtures as well?
It's applied to any material system, and we will have a very generic ways to describe it. So I'm not sure we have enough time to talk about that, but in the next class I will dive deeper to actually help you using the Flory-Huggins. Remember, we calculate what is delta G is. If you know delta G, we can basically do a very simple, beautiful math to understand when you're going to hit the spinodal point. Okay? So let's move on. No question for this part, right? Okay. So there are several unique cases where you would see different phase diagram. It's kind of very funky. Those two are the most common one. They call it lower critical point phase diagram, LCST. Why? Because if this is called a lower critical point in the phase diagram, okay, TC is here, which means at high temperature they're going to phase separate. At low temperature they're always going to be mixed, right? This is what we talked about at the beginning, where it's inverse, where at high temperature it will mix. So it's called upper critical temperature phase diagram, okay, or UCST. This one, how do we understand this? Nothing is there. Always mix. Great. This is a funky one. Only at the middle temperature it will mix. Too high or too low, it's not happy. It's like human being. They only want to stay in the air conditioning room. This is another weird one. Those few you only need to kind of know it's interesting, but not commonly see in a lot of material. Okay?
LCST because I guess I always associate heat as something that would help things mix together.
I do not know on the top of my head, but I certainly can do a quick search and give you a couple of examples. All right?
Okay.
So, let's give you guys some example. So, if you look at this particular graph, it shows transmittance, TR. This is one of the good methods. You measure how much transmittance you have, or if there's phase separation happens. So if you shine a light, or if you, let's say, for guys, anyone don't like the sun probation beer? Anyone? No?
I think everyone likes it.
Perfect. What is a breakfast IPA? Devil's Harvest?
Yep.
It's a little bit cloudy, right? That means there's a little phase separation happening there. Or they has some ingredient they didn't filter out and scatters light. So sitting here is when in the perfect mixed phase or uniform throughout the beer, it will be maybe the Suzy beer you can see through very nicely through the glass. That means light is passes through easily. There's no scattering of the light coming off. But if you start to have phase separation, now you have two material. You're going to learn it in Simon's class more, but let me tell you a little bit is when you have two components and they have four interfaces, then it starts going to bend the light to different directions. And this causes drops in transmittance. Or people call it the cloud point is where the things get cloudy. Right? So what this does is now if you look at different mixing of the material, if you increase the relatively ratio 1:2 to the phase diagram, see when they will become two phases. Does that kind of make sense for everybody? Okay? On here. Now the next question is even more interesting. Let's assume we have generic phase diagram look like this. Vertical, delta G, this is X2, volume fraction of the X2. This is not a phase diagram, okay? It's different. It's just a free energy plot, a different X2. Everybody can imagine how you get this? Pauli-Huggins equation. You know chi, you know temperature, you know the blend ratio, boom, everybody can do it, right? We just had a quiz. But now, if I ask you to do 100 times, instead of this particular point is 2 to 1, I ask you 1 to 1, 1 to 2. If you do, everybody do a calculation point, then we can pull it out to be this curve. Well, this is important because the shape of this is critically determines if your material will be stable at a given composition. And how do we do that? Let's show you an example as if we now have XA, XB, two of the ratio, 2 to 1 and 1 to 2 polystyrene polyethylene in two of my hands. Put it into the same jar, shake it. Will it mix or not?
Yes. Based on that graph, yeah.
Explain to me, Sam.
Because delta G molar quantity is less than 0 at all points.
Everybody agree? Do I need to explain a bit detail? Yes, let's do it. This is where component A, component B, when we mix them, what's the system in terms of free energy? It can be linearly calculated because we know component A and component B. It's basically follow this red line. It will fall onto this M point. So let's assume they're going to mix. It will be N1. if you just gonna go linearly, right? Or if I kind of give another example, if this is almost symmetric, you have A, B, 50-50, the free energy is gonna be average of 2, right? But that's just a hyper-theoretical value. If you look at this curve, at the same composition, you can find the system would adopt a free energy at M. Which one is higher? M star is higher. That means when you mix in, you would create an energy state of M star. But in reality, you can actually lower the system to fall on this diagram at N. You would release some energy and start to stable at this state. Straightforward, easy to understand. I can explain one more time, give you another extreme example. What if I start from 1 at here, 100% A, 100% B, and mix in 1-to-1 ratio? It will create, if there's no changes in the energy, after mixing, the system energy will be average of 2. Before mixing will be half of 0, half to 0, right? So it should be 0 right here. But because of the interaction, because of chi, because of entropy change, the real 50% energy stays here. So I can release this much energy, which is favored by system. I can go down the system state and stable there.
Is that like released as heat? Or what is that energy released as?
Probably you can consider it as entropy change and heat change. They're both related in the process, okay? So now, we know that free energy for 2 different states is linearly added together, so which means it's always going to fall on this line. We can move my pen differently. You can see any 2 data points, combination of 2 will be higher than on this curve, right? If you choose any 2 data points on the curve, draw a linear line, pick a middle point, it's always going to be lower than that. In other words, if I start with a single phase, listen to this very carefully, very interesting. If I start with one phase, I'm not going to separate myself into 2 because I'm favored than if I'm breaking into 2. Think about this reversely. If I start with M, can I separate myself into 2 states? This would be an example if I have one-on-one mixture in polystyrene polyethylene. Is it possible I break myself into 25-point polystyrene, 75 volume fraction polystyrene? Is it possible?
Yes,
Is it possible?
they're not like mixed fully, so you can still take components out of one that are specific to.
No, not going to happen. Because why? Because as I mentioned, we consider before and after. Before, I'm 50%, which is I stay at this end without star. This is where I start off. If I separate myself into 2 components, one going to be increase in the concentration, the other will be reducing concentration because I don't take anything out of it. It's just a phase separated into 2, right? Polystyrene rich, polystyrene poor. But adding together, they would have the same amount of polystyrene. We just separate it into 2. That's the case for the phase separation. If they phase separate, the total system energy will be M star. I would need to take energy to go up, then I can be split into 2. Make sense? I wouldn't happy to do that unless somebody give me the energy. When I would like to do this, give me an example. When I like to spontaneous phase separate. Let's don't talk about precipitation. It's a special case. Let's talk about phase separation.
Say you have two different specific heat capacities, you could bring down the temperature a lot and one would separate out?
Neither. Think about the phase diagram. This is only going to happen if you can drop the system free energy. Right? So before and after, the energy would drop. What if we have the delta G parabolic reverse, pointing down? Right now, it's pointing up. This we already talked about. Point down. The other one was going this way. So now, if I'm still the guy sitting here, we can use this point. This may be phi 1. Now, if I phase separate into phi 1 and phi 2, this is possible. I can phase separate into, let's assume this polystyrene rich. Phase separate into 2p's. What's the energy before phase separation? Is this one? G mix. Here, right? Once I phase separate, I go to this energy. Will you do this? Is it a good deal? Is it a good deal? It's a good deal. I lower some energy. So you would like to phase separate, because after phase separation, my total system energy is lower. So you sort of start to know one of the criteria if you want to phase separate is look at if the delta G plotted versus different phi value, if it's concave up or concave down. In those two examples, it's just very simple. You do either up or down. But in real case, you could be more complicated. Okay, we're going to talk more in the next class. But I want to leave you guys go home to think about one question. If my delta G is now with respect to volume fraction, it has both concave up and concave down. What's going to happen? Let's follow this chi equals 2.5. Just follow this curve. I have this behavior. Anyone want to give a try?
As you're going between the low and the max and the min, you're going to hit metastable in between.
Yeah, okay. So well, if I'm sitting here, do I like to phase separate?
Yes. No. No.
Yes or no?
No.
Why?
Concave up.
If I phase separate, I become these two, and I need to gain energy, right, to phase separate. How about going along this line? How about here? Hard to say. Here?
Yes.
I would like to phase separate into two, then I can lose energy. And now think about this one. This is basically capturing at a given one temperature. Okay, temperature is fixed. We only go from left to right. And how does this changes from single phase to two phase, like to phase separate. And then we will discuss more in next class how we actually reaches different delta G in those different states. And the only reason is shown here. Temperature make a difference. Because one guy has a booster while the other doesn't. So with temperature change, contribution from entropy will have trade-off. And this would causes at different temperature you would have different stages when they want to phase separate or not. Okay, I'll stop here, then I'll continue in the next class to explain the phase diagram. And next class goal is we will get the critical point using Flory-Huggins theory, find when this is going to happen, and when the spinodal line will happen and the binodal line. Okay? And we're going to have some homeworks so that we can get it started. Okay? So we're going to have question 1 to 6.
And,
It's going to do next Thursday, chapter 8.
Chapter
Chapter
7.
seven.
Use chapter 7.
Oh, 7, sorry. Yeah, 7. Okay?
Next Thursday.
Hmm? 1 to 6, and if you have a question you cannot answer, leave it there. And thanks for the feedback on that. I do feel like I need